Now, as I promised at the beginning of the lecture, we are going to derive the equation of the torque in terms of the parameters of the equivalent circuit. Let us start from the formula of the magnitude of the phase voltage, which is given over here. So it is equal to the product of the magnitude of the current in the rotor times the magnitude of the impedance in the circuit. So all of these in series. So remember, we are talking about the magnitude. That's why we have the square root, because this would be in a phasor form. And if we take the magnitude, we will need to take the square root. Also, remember that the power that has crossed the gap is given by this formula, and that the mechanical power is given by this formula, and it is related to the power that has crossed the gap based on this formula. Now remember the slip? It is the relationship or the percentage of the rotor speed compared to the synchronous speed. We can also calculate it by these speeds in radians per second. So these are exactly the same. So this is the synchronous speed in radians per second. This is the rotor speed in radian per second. And this is the synchronous speed in radian per second. Now, as we did before, the rotor speed in radian per second is equal to the synchronous speed in radian per second times 1 minus the slip. Where we are getting to, just bear with me 1 minute, and we will get to this equation of the torque. Now, remember that the rotor speed in radian per second is equal to 2 pi fsy, where fsy is the synchronous frequency. And this is equal to omega s, which is the electrical supply frequency multiplied by 2 over p, where p is the number of the motor poles, so the magnetic poles. And omega s is equal to 2 pi fs. Okay, so this is the relationship between the synchronous frequency, the electrical supply frequency, and the number of poles in the motor. We have just mentioned in the previous example that the mechanical torque is equal to the mechanical power divided by the speed of the rotor. Now, if we plug this formula over here in place of the mechanical power, we will get this. And then if we take the formula of the rotor speed, which is here, we put it instead of the rotor speed, we will get this. Now notice that this is a common factor. We subtract it out, or we cancel it, divide it out. We will end up with the power gap divided by omega SR. But again, omega SR is equal to omega S times 2 over P. So if we rewrite it, we will end up with this. So this is the first equation of the torque. But then we want to relate it to the parameters or the components of the circuit, which are the resistors and the equivalent reactance. So what we can do, after arranging these terms, we will replace the power that has crossed the gap with its formula that we just mentioned over here. So the torque would be this. But then if we expand the current in the rotor based on this formula, we will have the final equation of the torque. Now notice that the equation of the torque, it relates the effect of the resistor of the rotor, the slip, the frequency, the phase voltage, and the stator resistance, as well as the inductance reactance. It relates their effect on the mechanical torque. So in here, omega S is the electrical supply frequency in radians per second. And notice that the torque is proportional to the square of the supply voltage, Vs. And if we desire to keep Rs and the equivalent reactance to a minimum, we will maximize the motor torque. This is one way of increasing the motor torque. However, there is a complex relationship between the torque and the slip. And that's why we have the different shapes of the torque and speed or slip curve that we have seen earlier. One thing to keep in mind that the magnitude of the rotor resistance has opposite effects on the torque production at standstill and at rated speed or slip. So in order to overcome the problem of low efficiency, the first solution is to have a limited variable speed range. This would be, in this case, the supply frequency will be fixed, and this gives a high efficiency machine operating at a low slip, and therefore it will be a fixed kind of speed. The other solution is having the synchronous speed to vary at between 0 and the synchronous speed, and this will produce a high efficiency. And this can be done by varying the voltage and varying the frequency. So this is done by a variable voltage and a variable frequency driver. And in this case, any combination of the voltage and the frequency can be used to supply the motor with the condition that operation should remain within the limits of rated voltage and frequency. And in this case, by adding a power electronic converter, this can control both the supply voltage and the frequency of the motor. However, even if we change the voltage or the frequency, if we have their ratio constant, we can ensure that the flux induced will be approximately constant, and this will lead to constant load torque even if operating at different speeds. So to control the magnitude of the motor voltage such that the RMS voltage is proportional to the synchronous frequency, we can let the motor produce constant load torque with almost the same slip over a wide range of variable speed operation, and this is by changing the voltage or the frequency, however, keeping the ratio of them constant. So you can see that there is quite a lot of variety of motor types, and we can control its operational performance by controlling its voltage and frequency, and we can have an idea on what torque we want that motor to operate by understanding the parameters that affect the equivalent circuit. Alright guys, so we have reached the end of the lecture today. I hope that you have gained some knowledge on how to calculate the parameters of the equivalent circuit and how to analyze the performance in terms of power of and torque and efficiency of the motor. In the next lecture, we are going to look at another type of electric machines, which are the electric generators. Until then, have a lovely day, and I will see you next week. Bye.